temperatures reaching thousands of degrees, an environment with almost no oxygen, and dozens of continuous processing stages. That's what it takes to produce carbon fiber, the remarkable material found in the Boeing 787 Dreamliner, Falcon 9 rockets, Formula One race cars, and countless other advanced technologies. Stronger than steel, yet lighter than aluminum, carbon fiber has transformed the way we build aircraft, spacecraft, and other high-performance equipment. But how are ordinary polymer fibers transformed into a material with such extraordinary strength? Let's explore the manufacturing process and the story behind carbon fiber. The story of carbon fiber began with a completely accidental discovery. In 1958, during an experiment at Union Carbide, scientist Roger Bacon accidentally broke a piece of graphite. Inside, he discovered extremely thin carbon fibers, unlike anything that had ever been seen before. But with the technology available at the time, the estimated production cost was around $20 million per kilogram, making the material almost impossible to commercialize. 3 years later, Japanese scientist Akio Shindo made the breakthrough by using a polymer called PAN to produce carbon fiber. In 1970, Toray acquired the technology and continued improving the manufacturing process. Interestingly, the first commercial product was not an airplane or a rocket. It was golf club shafts, first sold in the United States in 1973. The sports industry helped keep the technology growing. But what actually happens inside a factory to turn ordinary polymer fibers into carbon fiber? The journey of carbon fiber does not begin with carbon. It begins with PAN, or polyacrylonitrile, a synthetic polymer that looks almost exactly like ordinary white thread. First, the PAN is pushed through thousands of tiny holes in a metal plate called a spinneret, creating fibers much thinner than a human hair. These are called precursor fibers, the raw material for everything that follows. Next comes stabilization. The fibers are heated in air at 392 to 572 degrees Fahrenheit for anywhere from 1 to several hours. The straight molecular structure of PAN gradually changes into a ladder-like structure. Without this step, the fibers would simply melt in the next furnace. Then comes the most important stage, carbonization. The fibers are heated to 2,192 to 2,912 degrees Fahrenheit in a pure nitrogen atmosphere with no oxygen. Almost all of the hydrogen, nitrogen, and oxygen atoms are removed. What remains is almost pure carbon, with a carbon content of over 93%. This is also the stage where the original white fibers turn into the familiar black carbon fibers. Finally, the fiber surface is chemically treated to improve bonding, then coated with a protective sizing layer to prevent damage during handling and manufacturing. The exact temperatures, heating rates, and fiber tension are closely guarded secrets. Even a small change in these parameters can produce carbon fiber with completely different properties. But there is one thing that most people misunderstand. Carbon fiber is almost never used by itself. What you see on a Formula One race car, an airplane wing, or a racing helmet is not pure carbon fiber. It is carbon fiber reinforced polymer, or CFRP, a composite material made by combining carbon fiber with epoxy resin. Here's how it's made. Thousands of thin carbon fibers are woven into sheets that look much like ordinary fabric, except they are black. These sheets are then soaked with liquid epoxy, pressed into a mold, and heated until the resin cures. The result is a lightweight, rigid material that can be shaped into almost any form. Why combine it with epoxy? A bundle of carbon fibers is extremely strong when pulled along the direction of the fibers, but it cannot hold its shape by itself and is much weaker when forces come from different directions. The epoxy fills the spaces between the fibers, spreads the load across the entire structure, and bonds thousands of individual fibers into one solid piece. In other words, when we talk about carbon fiber, in airplanes, race cars, or bicycles, we are usually talking about CFRP, a composite material, not carbon fiber by itself. What makes CFRP so special? Very few materials offer both the strength of steel and a weight much lower than aluminum. Carbon fiber delivers both at the same time. But here is the part most people don't know. When a force is applied along the direction of the fibers, carbon fiber is incredibly strong, almost impossible to pull apart. But if the force comes across the fibers, its strength can drop dramatically, even though it is the exact same piece of material. This property is called anisotropy, which means its mechanical properties are different depending on the direction of the load. This makes a huge difference in engineering. If you simply replace an aluminum part with carbon fiber while keeping the same shape, without redesigning the fiber orientation, the new part could actually be weaker instead of stronger. That is why carbon fiber engineers do more than choose a material. They carefully design every layer of fiber and every fiber angle so the loads travel in the right directions. A Formula One monocoque can contain dozens of carbon fiber layers, each placed at a different angle, with every layer serving a specific purpose. Carbon fiber is more than just a material. It is a language of engineering design. So, where is this language of design being used? In the sky, the Boeing 787 Dreamliner uses CFRP for about 50% of its primary structure, helping it reduce fuel consumption by more than 20% compared to the previous generation. SpaceX also uses carbon fiber in its payload fairing, the protective shell around the payload, because every kilogram saved at the top of a rocket significantly reduces the amount of fuel needed for launch. On the ground, wind turbine blades longer than 45 meters cannot rely on fiberglass alone. They would simply become too heavy. Carbon fiber is used in the main load-bearing spar to reduce blade weight by about 25% while maintaining the stiffness needed for continuous operation. On the road, electric vehicle manufacturers use CFRP to offset the weight of large battery packs. In Formula One, the monocoque cockpit is built almost entirely from carbon fiber composite. It is strong enough to protect the driver at speeds of over 186 miles per hour while weighing only about 77 pounds. Carbon fiber also improves everyday life. It is used in prosthetic blades for Paralympic athletes and in the frames of Tour de France racing bicycles. Interestingly, the sports industry was also the first market to successfully commercialize carbon fiber. Even today, it remains one of the material's most important applications. But who controls this material? The global carbon fiber market is worth about $4.4 billion and is dominated by only a few companies. Toray, Teijin, and Mitsubishi Chemical together produce roughly half of the world's high-quality carbon fiber, while Japan and South Korea supply more than 80% of the high-grade PAN precursor used to make it. Although China now leads in production capacity, aerospace is driven by certification, not volume. Once a carbon fiber supplier is approved for an aircraft program, it often remains the supplier for 20 to 30 years. In this industry, trust matters more than price. But carbon fiber has one problem that few people in the industry like to talk about: Producing 1 kilogram of carbon fiber generates about 20 to 35 kilograms of CO2, far more than producing the same amount of steel or aluminum. And when an airplane or a wind turbine reaches the end of its life, CFRP still cannot be recycled efficiently in most cases. As a result, much of it ends up in landfills or is treated as industrial waste. That is the paradox. A material that helps the world use less energy is also one of the most energy-intensive materials to produce and one of the hardest to deal with at the end of its life. But that is beginning to change. 2 major approaches are being developed. One uses very high temperatures to separate the resin from the carbon fibers so they can be recovered. The other uses chemical solvents at lower temperatures to preserve more of the fiber's original strength. Both technologies are still being scaled up, but the early results are promising. Since 2024, McLaren has been testing recycled carbon fiber on its Formula One race cars as part of its goal of building a fully circular race car by 2030. The next race for the carbon fiber industry is no longer about making the material stronger. It is about making it cleaner. Carbon fiber is not a truly environmentally friendly material. It takes a huge amount of energy to produce, and recycling it is still a challenge that has not been fully solved. Yet, this is one of the biggest paradoxes of the 21st century. Some of the world's greenest technologies are being built on a material that is not truly green. And carbon fiber is perhaps the clearest example of that paradox. The next battle will no longer be about making carbon fiber stronger. It will be about making it cleaner. That could become the next great materials revolution of the coming decades. If you enjoyed this video, don't forget to like and subscribe so you won't miss future stories from Mido Explained.